Now we're ready to begin college algebra, finally, after the review. I wanted to say a couple of things before we start the topic that is currently on your screen, the word graphs. I'll talk about that in a moment. The first thing I wanted to mention was be sure and read your book. Don't try to do college algebra by only looking at the problems and working from them to the rest of the text. Read the text. This is a very good text. It's worthwhile reading. And also read all of the notes that are provided to you. I think that'll be very worthwhile. Secondly, realize that this is a video. If you don't follow something the first time, feel free to rewind it and replay it. This is not something you can do in a classroom, but you can do here. So please keep that in mind. Now, on to the first unit of college algebra, which I will call graphs. And you might ask yourself, why are we starting an algebra class with graphs? Well, algebra is intimately related to visualization. And with modern technology, specifically graphing calculators and computer software, we can graph things more easily than we ever could. And so we can get that visual insight in addition to the algebraic insight. So modern technology certainly helps us here. This is no longer the old college algebra course. Final note is that a graphing calculator is required for this course, as you'll see in the textbook. I will use a particular graphic calculator. You may have different ones. I will not be giving any keystroke tutorials on calculators. I will keep my remarks as general as possible. And the kind of things we will be doing will be limited to those aspects of the calculator that are simple to use and common among the calculators. So you shouldn't feel that you need to have the machine that I use. So, having said that, let's go on to the course. Starting the first unit, graphs. All right, the first topic I'd like to talk about is rectangular coordinates. That is where the graphs will be drawn. And this is an example of where geometry meets algebra. This is really something that is part of analytic geometry. All right, so let's look at rectangular coordinates. Rectangular coordinates. Now you will see that this is sometimes referred to another way, and I'll put that just over here on the side. These are sometimes called Cartesian coordinates because Descartes, René Descartes, was one of the people that invented it back in the 1600s. But we'll just call them rectangular coordinates. Now, before I draw them, let me recall something from the review where we talked about the real number line. Remember the real number line. We drew it something like this. We put a 0 at one point, and we marked off units, and all the real numbers then lived on this line. So this was a representation of the real numbers. This is a one-dimensional object, and every point on this line has an address. Another word for that is coordinate. If I want to know where this point is, I simply find out what number is associated with it. So every point on the line has a numerical address. This is one dimension, so this is r, and you can think of this as r to the 1 power. Now what we want to do is move on to 2 dimensions. So we have space, just like this sheet represents 2 dimensions. It will require 2 numbers to indicate where a point is. And the way we will do this is we will first of all lay down a copy of the real number line here. Here's where I will put the 0. And I won't draw in the other numbers right now, but you know that they're there. And then I will erect another real number line at some angle to this. Now it doesn't matter what angle I use. I could have the second axis be at an angle like this. I won't because the convention is to put it at right angles. But theoretically it makes no difference. Now what have I done here? I have 2 copies of the real number line. It would help now if I put some numbers on there. So let me do that. The real number line that is horizontal will be numbered in the usual fashion, with the positive numbers going to the right and the negative numbers going to the left. This axis is usually referred to as the x-axis. You can, if you like, call it the horizontal axis. Horizontal axis. The other axis will be referred to as the y-axis, although If the variables that you are working with change, these need not be called x and y. They can be called other letters. But these are the traditional letters for now. And the y-axis, of course, can also be referred to as the vertical axis, which is probably safer. Now, how am I going to put the numbers on the horizontal axis? Well, the tradition is to make the positive numbers go up and the negative numbers go down. And that is how the number line is marked vertically. Now, what does this do for all of the points in the plane? I claimed that this was a way of giving them addresses. Well, it's easy to see how this works. For example, let me pick a point over here, which is in a nice position. You'll notice that to get to this point, I have to first go 2 units over to the right. That's what the 2 here, my little 2, which is hard to read, my 2, and then I have to go 1 unit up. So we will begin to label these in a way that takes into account that it's 2 units to the right and 1 unit up. I will write the 2 first and the 1 second. We'll talk about this later on, but you can think of this now as an address. This point has this address. And notice that the placement of the numbers matters. If I reverse the numbers and I go over a distance 1 and then go up 2, I come to another point. This point I would have the address 1, 2. Now I think you see the pattern that's developing here. I'm putting the number that comes from the x-axis first and the number that comes from the y-axis second. Let me do one more to show you what I mean. Let me come over to this point. It is on the x-axis, whoops, that's a -2. On the x-axis, -2, and on the y, going down here to -1. Now these were only points that had whole number coordinates. That's what we call these individual numbers, coordinates. But there are, of course, all the other points in the plane. And they all have coordinates of their own, whether or not they're whole numbers. So all points in the plane now have an address. There are other parts of this picture I want to label while I'm here. This point at the center, it's probably worthwhile to indicate what this is called generally. This is usually referred to as the origin. Of course, it has its own coordinates, 0, 0. But it is referred to as the origin. Now, if we look back at the number line for one dimension, this number line, we could call this point also the origin. But it is not that distinctive because 0 is a perfectly good label here. However, in 2 dimensions, 0, 0 is the point, and so we tend to refer to this as the origin. And remember that the axes are placed at right angles strictly as a matter of convention. This is now 2-dimensional, as opposed to 1-dimensional real number line. This is sometimes referred to as r squared. That's the entire plane is called r squared. That's just a name. There's nothing particular associated with that. All right, this picture is getting a little cluttered now, so let's make some other notes. Points have addresses, as you saw on the previous page, of the form x, comma, y. This is the first coordinate. It's also referred to as the x coordinate. And likewise, this is the second coordinate. And the order matters here, also called the y coordinate. And this pair is referred to as an ordered pair for obvious reasons. The numbers are ordered. Which one comes first matters. Now you might look at this and remember something from the review. You say, no, wait a minute. Didn't we use this same notation for interval notation, for an open interval going from x to y? Yes, we did. Unfortunately, it is the same notation. But in context, you will not confuse this. So let's go back to our picture in 2 dimensions. I will probably not write the little arrows at the ends of the lines anymore, but I will label the axes. This will be called x and this will be the y-axis. And I will only put numbers on these two lines when I need them. Now, there are some other parts that need to be labeled here. These two lines divide the plane up into 1, 2, 3, 4 pieces. These 4 pieces are given names. They are called quadrants because quad refers to 4. This one is the first quadrant. This is the second quadrant. This is the third quadrant. And this is the fourth quadrant. And believe it or not, traditionally, Roman numerals like that are used. One of the few uses of Roman numerals you'll find anymore. The logic is that you're going in a counterclockwise direction to label the quadrants. A couple of other things I'll draw here, even though I've mentioned them before. If you go to the right on the real number line that is horizontal, that is the positive direction for the x's. If you go up, that is the positive direction for the y's. And of course, if you go to the left, that's negative for the x's, and if you go down, that is negative for the y's. So that gives you visually an idea of what's going on. Rightward is positive or upward. Left or down are negative. The next thing I would like to look at is the distance between points. We are now in the plane and we have all the points given addresses, so now we can sensibly talk about the distance between points. So, distance between points. And this will remind you of something that we talked about in the review. So, the question naturally is, what is the distance between 2 points that I'm given? So, what is the distance between 2 points? Well, points have addresses now, so let me use their addresses. Between x1, y1, say, and x2, y2. Now please realize that these numbers 1 and numbers 2 are subscripts. They are little labels. They are attached to the variable. They're not multiplied or anything else. So the question is, what is the distance between, say, those 2 points, wherever they may lie? Well, let me draw a picture in the plane that illustrates more or less the general situation. It can't be completely general, but I think we'll cover most of the bases here. So I draw the x and y axes, and I'll just imagine that one of the points is here and the other point is up here. Now let me call the one on the left for no particular reason. Let me call that x1, y1, and I'll call this one up here x2, y2. And since those are the numerical addresses, I might also want to refer to these as point P1 and this is point P2. That will just make the notation easier. Now my question is, what is the distance between those 2 points in the plane? And I will label that distance as d P1, P2. And that's what I'd like to figure out, what that number is. Here's how I'm going to do it. I'm in a plane that has 2 coordinate axes, a horizontal axis and a vertical axis. If I draw now a line that is parallel to the horizontal axis from the first point, and then one down which is parallel to the vertical axis, you see that I've created a right triangle. This is a perfectly legitimate right triangle. And I can also, by the way, label this point, because I see that it is the same distance over on the x-axis as this point is. So this must have x-coordinate x2. And it's the same distance up all along here as this point is. So y1 would be the other coordinate. All right. Now, remember I'm trying to find this distance. Well, once I've drawn a right triangle, you should remember the Pythagorean theorem, which says that if I want this distance here squared, I simply have to find this distance and add them squared. So let's see what those distances are. Well, this horizontal distance, is at the same height, y1, all along the way. So if it is x2, x2 is here, and x1 is here, what's the distance between those two? We discussed that in the review. It's always going to be x2 minus x1. So this distance is x2 minus x1. Now, there may be someone out there saying, now wait a minute, what if this point is over here? What if the points are reversed? We want to have this be general. So what I'll do is, instead of writing x2 minus x1, I will just write the absolute value of the two, of the difference. Now that's always positive, no matter which way you go. x2 minus x1 or x1 minus x2, the absolute value is positive. And after all, a distance is a positive number, so absolute value is perfectly fine. Do the same thing vertically. This distance here, from here to here, a little hard to draw there, is y2 minus y1, because the height of this point up here is y2, the height of this point is y1. But I won't use this form, I'll use the absolute value version so that I don't worry about when it might be negative. So, with that information, let me go ahead and apply the Pythagorean theorem. By the Pythagorean theorem, which you remember from the review, I hope, the distance I am looking for, distance P1 to P2 squared, should be equal to the distances x2 minus x1 squared plus y2 minus y1 squared in absolute value. Now let me bring back the previous picture so you'll see what we're talking about. Here is the hypotenuse. Here is one leg. Here is the length of the other leg. And so the Pythagorean theorem says this must hold. Well, if I want the distance, I need to remove the square by taking the square root of both sides. And the other thing that I want to notice is that absolute value of a number squared is the same as the number squared, because when you square a number, the plus or minus sign becomes positive. So I can now rewrite this as the distance from P1 to P2 being the square root of x2 minus x1 squared plus y2 minus y1 squared. And there is a formula that will always give you the distance between any two points in the plane. The point x1, y1, and the point x2, y2. So let me illustrate this with a couple of examples. So here's one example. Want to find the distance between these two particular points, -2, -5, and say 1 and -6. Now I'm not going to even draw them because I don't need to. I have a formula now. And when I apply the formula, it makes no difference which of these I choose to be the first point. I will choose the one on the left because it's convenient, but it makes no difference. I'll get the same result either way. So just for the record, I'll call this the first point and call this the second point. Then the solution is the distance, I'll just write the word out, is going to be equal to, and let me fill in the formula now, the square root, and you know what it looks like. It's a square plus a square, so you can write that down. In the first one, I have the difference of the x values. So, treating this as the second point and this is the first point, I'll take the second x value, 1, minus the first one, which is a -2. And then here I'll do the same thing for the y's, -6 minus the -5 from the first one. Now let me move on to another sheet and continue my calculation. I have the square root. I have a thing squared plus a thing squared. See, writing down the structure like this often helps you do the work. Now let me remind you what we had. We had 1 minus a -2. Well, minus a -2 is +2, so 1 plus 2 is just 3. So all I have in here is 3. For the second one, I have minus 6 minus a minus 5. Minus a minus 5 is plus 5. Plus 5 minus 6 is minus 1. So in here, I have minus 1. Well, 3 squared is 9. Plus minus 1 squared is 1. So I have square root of 10. And that is the distance between these 2 points. Now, if you like decimals, I have gone ahead and approximated this on my calculator as 3.162. So there you have how you find the distance between 2 points. The formula is very easy to apply. Let's do a more interesting problem involving distance. This is the kind of problem you'll find in some of the homework. Example. Here are 3 points. A equal minus 2, 5. B equals 1, 3. And C equals minus 1, 0. And here's what I want to do with these points. I'll just list the directions, and then we'll go ahead and do all of these things. We want to plot each point. There's my abbreviation for point, by the way. And form triangle ABC. Abbreviation for triangle. Secondly, I want to show that triangle ABC is right. It is a right triangle. It is a triangle with a right angle. And finally, find its area. So there's what I need to do in this problem. We'll attack it piecemeal. First of all, we'll plot each point, and then we'll draw lines between them to form the triangle. So that is the first step. So here is the solution. And I will need an axis system, so I'll go ahead and draw my axes in here. Now, you can decide about how much you need by looking back at the points. Notice that the x values never get lower than minus 2 or bigger than 1, and the y values vary from 0 up to 5. So that gives you a sense of how much you need to have. So with that in mind, let me mark off 5 on the y-axis. So that's 5 units up. This is the y-axis. I know I need 1 at least on the x-axis, and then a couple on the negative side of the x-axis. And then the points, let me remind you what they were, minus 2, 5, 1, 3, and minus 1, 0. So minus 2, 5 is minus 2 and go up to 5. So there's point A. B is 1, 3. Here's the height 3. So that's point B. And then minus 1, this is minus 1, 0. The y value is 0, so we don't go anywhere. This is the point C. And now I just draw in the lines connecting these points, and I have formed triangle ABC. Now that was the first thing I was asked to do. Now when I look at this triangle, I suspect that this angle is the right angle that I'm requested. But to prove that this is a right angle, I am going to use the Pythagorean theorem again. I'm going to show that this is a hypotenuse, and if I take this distance squared, it's equal to this distance squared plus this distance squared. It's exactly what the Pythagorean theorem says. So I need to compute 1, 2, 3 distances and then see if they satisfy the Pythagorean theorem. So let me first compute the distance from A to B. Well, that's a large square root, and let me remind you what the points are here. A is the point minus 2, 5, and B is the point 1, 3. So the distance between A and B, of course, it's something squared plus something squared. Here I have the difference of the x's. Here I have the difference of the y's. I'll choose the first one to be the first point and this to be the second point. So 1 minus a minus 2. And here I'll put in 3 minus 5. 1 minus a minus 2, 3 minus 5. Be consistent. Well, now the rest of this is just simple calculation. 1 minus a minus 2 is 1 plus 2. That's 3. That's 3 squared I have here. 3 squared, of course, is 9. Plus 3 minus 5 is a minus 2. Minus 2 squared is 4. So I know that this is the square root of 13. And it does not pay to turn this into decimals at this point, as you'll see. You want to leave an exact answer. Well, let me do the others the same way. Let me add here the point C. To jog your memory, it's minus 1, 0. So I have the distance from A to B here, square root of 13. Let me do the next one, the distance from B to C. So that's the square root, difference of x's squared plus difference of y's squared. In this case, considering C to be the second one, minus 1 minus 1, quantity squared, and then 0 minus 3, quantity squared. Well, minus 1 is minus 2. Minus 2 squared is 4. Plus minus 3 squared is 9. Oh, look at that. It's also square root of 13. So I have 2 of the distances I need, and they are the same. That's hopeful. Let me do the last one. The distance from A to C is equal to the square root of difference of x's plus difference of y's. And if you remember what the x's are, let me rewrite that again here. A is minus 2, 5. C, remember, is minus 1, 0. Keep it all on the same screen. Then the difference of the x's would be minus 1 minus a minus 2. And the difference of the y's would be 0 minus 5. Well, again, this is simple. Minus 1 minus a minus 2 is plus 2. 2 minus 1 is 1. 1 squared is 1. Plus minus 5 squared is 25. So I have now the square root of 26. So I have the 3 distances. And I think you see already what's going to happen. Notice the following. That if you take the distance from A to C squared, I claim that that's equal to the distance from A to B squared plus the distance from B to C squared. And if you remember what those numbers were, this is the square root of 26 squared equals the square root of 13 squared plus the square root of 13 squared. And when you square a square root, of course, you get the number. So 26 equals 13 plus 13. Yes. Yes what? Yes, triangle ABC is a right triangle. And the right angle, to bring the picture back, the right angle is exactly the angle we suspected. The right angle is sitting at B. Okay, so the right angle is at B. Now, there was one other question we needed to answer. What is the area of triangle ABC? Well, let me bring the picture back. Here's the triangle as we drew it. Now we've found out the lengths of these sides, so let me mark them. This side is now square root of 13. This side, or leg, is the square root of 13. And this side is the square root of 26. Well, to find the area of a triangle, you take equals 1/2 base times height. In this case, it's 1/2. If I decide to take this as the base, that's square root of 13, and then at right angles to it is the height, also square root of 13. So I have square root of 13 times square root of 13. Well, of course, that's 13 halves. And there is the area of the triangle. If you don't like that as an improper fraction, perfectly good fraction, you can write this as a decimal. It turns out to be a decimal that terminates. It's a rational number after all, 6.5. And there we are. We've answered that entire question, which is just a long discussion of what distance is. Let's look at one more item, the midpoint of a line segment. And this will result in what's often referred to as midpoint formula. So I'll call it that here. It's a formula for computing the midpoint between 2 points. Well, once again, let me demonstrate the idea by drawing a sort of generic picture. Let me imagine that I have a point here and a point here. And I'll label the left-hand one x1, y1, and the right-hand one x2, y2, and then draw the line between them. And what I'd like to find is this point here. Call it M for midpoint. Midpoint. That's the coordinates I'd like to have. Now I have the coordinates of the endpoints. How do I get the coordinates in the middle? Well, here's the idea, and it uses a little bit of geometry. I'm going to do similar operation to what I did previously in proving the distance formula. Let me draw some lines that are parallel to the x-axis here. This is the x-axis, this is the y-axis. And then come up to the point that I want to be the midpoint and draw a vertical. This, of course, is a right triangle. And let me repeat the process starting at this midpoint and create another right triangle here. Now, these two triangles, I claim, are congruent. That is to say, they are identical triangles. Not too hard to see. First of all, this is the midpoint, whatever the coordinates are. So that means this side and this side are the same length, by definition. Now, how do I show that the rest of this is the same on both of them? Well, let me demonstrate part of it to show you what's going on. If I extend this center line, and let's see, yes, and extend this line, and extend the line I'm looking at, these two lines here are parallel, and this slanting line is a transversal, as we call it in geometry. It's a line that cuts across the two parallels. Now, the facts about parallel lines say that the angle that this makes with the one parallel is the same as the angle it makes with the other one. Now, that's a fact from Euclidean geometry, so these two angles are indeed the same. Well, the same idea works to give these two angles the same. Of course, you don't need that, because if this angle and this angle are the same, they already share a right angle. The third angles have to be the same. And if all the angles are the same and they share one side, the two triangles are congruent. So what does that mean? That means that, for instance, this vertical distance and this vertical distance are the same. In other words, the total distance, which is the distance from y1, this height, to y2, this height, if you cut it in half, will give you the coordinates of this point, because these two are the same. Likewise, for the x distances, this distance and this distance are the same. So that means the total distance from x1 to x2, over here, there's x2, there's x1, the total distance is cut in half by the midpoint. So with those observations, it's easy to write down the midpoint formula. So, the midpoint between, let me write out the entire process here, between x1, y1 and x2, y2 is a point x comma y, which has the following coordinates. Each one is exactly halfway between, and so that's the average. 1/2 x1 plus x2, and the second coordinate is 1/2 y1 plus y2. So there is the midpoint formula. This point here will always be exactly between x1, y1 and x2, y2. It will lie on that segment, that line segment, and will be exactly between. Notice that these are the averages. 1/2 x1 plus x2 and 1/2 y1 plus y2 are the average points. So let's do an example on this to show you how this works in practice. Let me take 2 points, say -5, 3, and the point 3, 1. Let me draw the picture and also compute the midpoint so I can convince you that that's right. First, I'll compute the midpoint, and then we'll see what this looks like in the picture. the midpoint by the formula should be the following large point: 1/2 the sum of the x's. So that's -5 plus 3. And then 1/2 the sum of the y's, which is 3 plus 1. Well, we simplify that. That's 1/2 minus 5 plus 3 is -2. And then 1/2, 3 plus 1 is 4. And then finally, we have the point -1 and the point and the coordinate 2. So I claim that this point is the midpoint between these 2 points. Let me convince you by drawing a picture of all 3 points. One, 2, 3, 4, 5. That gives me -5 in that direction. 1, 2, 3. There's one of the points, the -5, 3 point. The other point that I was given is the point 3, 1. So there's 3. This is a height of 1, so there's the point 3, 1. Here is the line between them. And the midpoint is supposed to occur. Remember, the midpoint was calculated to be -1, 2. Here's -1. Here's a height of 2. There's the point -1, 2. And it certainly does appear to be exactly between those 2 points. So I've computed the midpoint in a fairly easy fashion. So that's a formula that will be handy later on. Now it's time for us to look at the next topic, which will be your graphing device. Now we're going to go ahead and look at your graphing device, which is the title I've given to this bit of this unit. Graphing device probably refers to a graphing calculator. As I said earlier, a graphing calculator is required for this course. You may have access to a computer algebra system, but I will assume only a graphing calculator. And as I've said before, it doesn't matter what graphing calculator you have. Any graphing calculator will do for this. They all share the same features that we will be using. I will give you a mild introduction to those features, but I will not give you the keystrokes for using those features, because that differs from calculator to calculator. So let's go ahead and look at your graphing device. On your graphing device, the most important thing for us at this time will be the screen in which the graphs appear. Now the screen is more or less this shape on most of the calculators you see. And if you have it set up so, say, the y and the x-axis here appear in the center of the screen, it will look something like that. Now we need to have some sort of common markers for this, some labels that we commonly use, so that I can refer to pictures like this and we all are saying the same thing. So you notice you have the x-axis here. The x-axis is not full, of course. It has a starting point and an ending point, so there really is an interval here. And the way this is traditionally labeled, now that we have these calculators, is this end is usually labeled x min for the minimum value of the x's, and this end will be labeled x max. And similarly, the top will be labeled y max, and the bottom will be labeled y min. And that gives me the 4 dimensions I need, which describe what this is, which is a window. Right? Let me put that up here. This is a window. And I'll examine that idea a little bit more in a few minutes. Now, what else would I like to have on here? Well, sometimes you want to have tick marks, these little marks here, to indicate where certain numbers are indicated on the screen. And so what we need to do is decide how far apart these are. So there's a notation for that too. If this is the distance between 2 of the tick marks on the x-axis, that will be referred to as the x scale, and it's often abbreviated like this, SCL. But it means the scale. And what is it? Well, it is the number of units per tick mark. Now, tick marks are these little marks along the line. And if the x scale is 1, that means this is a length of 1. The x scale is 2, this is a length of 2. The x scale is a half, then this unit here measures a half. The same thing goes for the y direction. And of course, as you might expect, this will be called the y scale. And this will be the number of units per tick mark on the y-axis. So those are these are the 6, x min, x max, y min and y max, x scale, y scale. These are the 6 variables you need to set when you're trying to describe a window in a graphing calculator. So let me go ahead and discuss how one would write these down. We draw them as follows. This is the standard way of drawing these. Now you're going to be drawing these, you're going to be copying them off your calculator onto paper. And there are 2 standard ways to do this. Either this way, so here is the window, and maybe here are the axes. We would write -3 to 2 for the x min and the x max, just write them at the ends of the x-axis, and -4 to 5, say, for the ends of the y-axis. And then the graph, whatever the graph is, would be in here. So that's one way of indicating the window. There is one other way, and I will use these 2 ways interchangeably. There is one other way to do this that has become standard as graphing calculators have become standard. Again, I'll put the axes in here. And that is not to mark the numbers on here, but rather to indicate below that there's an x-axis distance from x max to x min and a y-axis distance from y min to y max in this manner, by writing 2 intervals, closed intervals, with a cross in between. The first interval always indicates the x values, so this would be -3 to 2, indicating x min to x max. This would indicate the y interval from -4 to 5, y min to y max. Now this is a shorthand form that often appears when people are stating problems or stating problems for a test, or sometimes in textbooks it'll appear this way. So be aware that there are 2 ways to do this. You probably will like the first way for most of the work that you use. Now, there is one thing I can note based on the screen before we actually see any of these. There's still some things we can say. Let me draw another example of a window here, and let me be very, very careful to indicate some tick marks here. And I will go 1, 2, 3, 4, and 5 will be the very top. Then 1, 2, 3, and 4 will be the very bottom, so that's -4. I will go 1 to 2 here on the right, and then -1, -2, -3 over here. So there are the same numbers I used before, except now I've marked the tick marks. Now you can see that the scale on the x-axis, on the y-axis here, the vertical axis, these seem to indicate 1 unit because there are 5 here and 4 here. They are also 1 unit on the x-axis, although they are different sizes. Now that's something you have to get used to. Both of these represent a single unit, whether it's vertically or horizontally. Now, with the tick marks on here, if I mark a point there, I can read off the coordinates of that point simply by seeing where the 2 coordinates hit the tick marks. So this would be the point 1, 3, because this is the point 1 on the x-axis, and this is 3 on the y-axis. And then, of course, if I had a point down here, say, I can read that off of there also. And this is the kind of practice that you want to do in the beginning to make sure you're clear on how the screen works. There would be a point there, and this would be -2, because that's 2 units to the left on the x-axis, and then down 3. You can see this is -3, and that would be the point -2, -3. Now, one other note I want to make while we're here talking about points on the screen. The very smallest possible point on a screen is what's called a pixel. It's a slang term that has come from picture element. What it is a very tiny square. I've drawn one here that's much larger than it would normally appear. A tiny square, and that is the smallest unit on the LCD panel that makes up the window of your calculator. So you will not have the kind of depth that you might have on a computer screen because the pixels are larger on here than they would be on a computer screen. And of course you don't have the infinite depth that you'd have in the mathematical 2-dimensional plane. So be aware that the machinery has limitations. All right. Now I want to make a point about windows. I said I would do this. Let me do this now. Here I'm going to first of all draw freehand. There's the x-axis, the y-axis. A curve with some interesting parts here. All right, there's a lovely curve. Now, Finding a window is crucial. And here's the reason why. I have cut out here a black piece of cardboard, and now I've placed it here at the center. And you can see that what I've marked here is a window, the size of a graphics calculator screen, for example. Now, the window will determine what you see, and that's why you have to be very careful about the windows you choose. And in fact, what we want to do in the end is learn to choose the best window so that we can see everything about the graph. As I have it set right now, you see the y and the x-axis, and you see a piece of the curve. If the window were placed over here, the curve would look very different, wouldn't it? If the window were placed over here, the curve would look different again. If it's placed down here, different again. I hope you begin to see the point that where you place this window is going to determine the kind of picture you see and how much of the graph you can see within the space you've indicated. So it's your job to find the best window to look upon this world of two dimensions in which the graphs live. So we will be talking a lot about that. And in fact, the way to find some of the most interesting points, like there's a peak there and a valley, these are very important points you'd like to know about. Some of this can only be done once you have calculus. But there's a lot that can be done with college algebra, and we'll talk about that. So that was my point about windows I wanted to make clear. Now we're going to actually look at a couple of calculators. Now here's the first of the calculators. First thing I'm going to do is turn it on. And you can barely see up in the upper left-hand corner here a small cursor. And that is the screen where people would normally do regular calculations, scientific calculator calculations. I don't want to look at that today. The first thing I want to do is tell you that every one of these calculators has some sort of setup screen. This is the setup screen for this calculator. It is the screen in which you set up the basic parameters you want to deal with. Now, I'm not going to examine all of these. I'm interested in one in particular, the one that says coordinate system. And if you look over to the right, it says rectangular coordinate, and then there's parametric coordinates, polar coordinates, and sequential. We will do rectangular, so I want to make sure that that's highlighted, and so it is. And that's all I need, so I will just leave it at that. Now I want to go ahead and look at another key. There's a key here called window. On your calculator, it may be called range, although window seems to be common these days. And this is the window I was talking about. You can see on the screen that there's x minimum, x maximum, x scale, y min, y max, and y scale. These are the things that you set. And let me go ahead and show you how you might set these. For example, I might type -4 and then enter 4 and enter. That takes my x scale from -4 to 4. My interval from -4 to 4. The scale I'm going to leave at 1, as you see. Then the y min is already -4, the y max is 4, the y scale is 1, and so if I now hit the key that says graph, I have a screen in which the tick marks are reflective of the x max and x min, the y max and the y min. Now there's no graph on there yet, and I don't want to do a graph just yet. We'll talk about this later. But I wanted to show you what this looks like. This is an example of a screen that is fairly dense with pixels. There will be a lot of resolution on here, and we'll talk about that later. But I wanted to go ahead and show you yet another calculator where the resolution is not quite so good. It's on this calculator. Let me turn this on. Once again, we're in a screen where you do calculations. I will now go over to the graph screen. It asks me for an equation, but I don't have one. And there is a graph screen. And I could set the window here also. On this one, if I hit the key that's called range, you notice that I don't have as much information on a single screen. That's because there aren't enough pixels to hold it all. I can do x min, x max, x scale, and then if I keep going down, it switches to y min, y max, and y scale, and I can set that. Now that's all I wanted to show you on these two right now. We'll be coming back and spending a lot of time on these. But now let's go back to the pad and talk about a few other things. So, on the pad, I want to indicate on the graphing calculators there are some keys that you should know. And when I finish this, we'll stop the tape and you can have a chance to explore the calculator that you happen to have. There's some keys to know. These are not scientific calculator keys. These are keys that are peculiar to the graph and calculator revolution. The first one is the variable key. And I'll give you 3 ways that I have seen this key look. There's one way with x, theta, and t, because remember the coordinate system could involve x's and y's, or be polar coordinates, or be parametric coordinates. There are others that look like this, x, t, theta, and n, in which sequences are a possibility. And then, of course, another version, x slash t slash theta slash n. And you see that they're all in the same ballpark. They're all identically variable keys. And depending on what coordinate system you're in, when you hit this key, you get the appropriate variable. So you don't have to choose that. Secondly, there are keys for graphing. There is a key that's become common these days. It's the y equals key. That's where you type in the function or the equation that you're trying to graph. Then there is a window key. That is the key in which you set the window. We've already talked about that. Sometimes, as I said, this is called range. You have to look at your own calculator's user manual to find out which. There will be a key called graph or something of the sort. And that is the key you hit once you've set your window and you've typed in your function for it to graph the function. When you're typing in your function, there is a key called math that seems to be common on most calculators, in which you get the symbols that you use to type in various complicated functions. If you're typing in trigonometric functions or other sorts of things, you can get those symbols there. There is also another key that has become common. It's called trace. We're going to talk about this at length later. This is a key that allows you to follow along the graph, to have the cursor. Remember what the cursor looks like on these. It's a little cross. To have the cursor follow the curve and tell you the coordinates of the point of where the cursor happens to be. So that's trace. I'll move over here to get a few more on here. Zoom is another aspect of graphing calculators that allows you to adjust the window in wonderful ways. You can zoom in, you can zoom out, and this is something that you can't do with graphs on paper, of course. There is also a key very often, or access to a key via some second function called table, in which a table of values can be showed for a particular function. This is also very handy. And one other small note, there are usually 2 keys on your calculator. One is usually indicated this way, which is for subtraction, and then there'll be another one. So this is versus another one. Sometimes it's indicated this way, or you'll sometimes see it as minus x. That is the key for negating a number. Now that's different from subtraction. The calculator forces you to know the difference. And so this is something you want to be sensitive to. Now let's leave these on the screen for a moment. These are the keys that you need to know. So what we're going to do now is we're going to stop the tape, and you can spend some time learning about your own calculator. When we come back, we'll do some more with the calculator and continue on with this unit.